Welcome everyone. In this lecture, I will discuss about acoustics. Here we will cover acoustics and its importance, reverberation time, Sabin's and Eyring's formulae, absorption coefficient, method to measure absorption coefficient, applications of acoustics, that is designing of hall for speech, concert and opera. In this part, I will discuss about acoustics and its importance and reverberation time. The word acoustic is derived from the Greek word acoustikos, meaning off or for hearing or ready to hear. In fact, hearing is one of the most crucial means of survival in the animal world, and speech is one of the most distinctive characteristics of human development and culture. Accordingly, the science of acoustics spreads across many facets of human society, that is music, medicine, architecture, industrial productions, warfare and more. Acoustics is basically a branch of physics that deals with the study of mechanical waves in gas, liquids and solids, including topics such as vibration, sound, ultrasound and infrasound, and certainly deals with the production, propagation, transmission and detection of sound waves. So sound is basically a form of energy that is produced by vibrating bodies. But do we hear sound of every vibrating body? The simple answer is no. We have two types of sound, audible sound and inaudible sound. These are categorized on the basis of their frequency ranges. Human ear cannot detect sound frequencies less than 20 Hz, that is 20 vibrations per second, and above 20,000 Hz. So any sound below this frequency will be inaudible sound for us. And this low frequency sound which our ear, that is human ear, can't detect is known as infrasonic sound. Sonic is actually the Latin synonym, after which the term sonics used to be a synonym of acoustics. The higher range inaudible frequency, that is above 20 kHz, is known as ultrasonic sounds. So anything in between 20 to 20,000 Hz is audible sound. So now we need some unit to measure sound level. Decibel is actually the unit which we use to measure the sound level. It is actually the ratio of the power at the output Y and the power at input X. Instead of indicating this ratio linearly, often the logarithm of base 10 is used. You might want to know the approximate sound levels of some common sounds in air. You can see here the sound levels of some common sounds, all relative to intensity of a sound wave in air with a pressure of 20 micropascals. For instance, normal breathing is around 10 decibel, quiet conversation maintaining the social distance is around 30 decibel, the sound of the car is around 70 decibel, hair dryer is around 90 decibel, helicopter sound is around 100 decibel, the siren of the police car is around 120 decibel, and the sound of the jet engine is around 130 decibel. So up to approximately 40 decibel it's faint sound, 40 to 60 decibel is moderate, 60 to 80 decibel is loud, 80 to 110 decibel is very loud, and approximately above 110 or 120 decibel is extremely loud and painful. So sound is a mechanical wave and therefore requires a medium to travel. So it is reflected, transmitted or absorbed by materials it encounters. So there are different kind of materials. For instance, there are soft surfaces that are textiles or the bat insulation. These actually absorb sound waves, preventing them from the further motion. There are hard surfaces, for instance ceramic tile, gypsum board or wood. These actually reflect sound waves and causing echo. There are dense massive materials, for instance concrete or brick. These actually transmit sound waves through the material. So depending on our requirement, we can use different materials. For instance, if you want to build a soundproof home, you can use bat insulation between the framing of your home. A very interesting part of acoustics is architectural acoustics. Architectural acoustics, which is also known as room acoustics and the building acoustics, is the science and engineering of achieving a good sound within a building and is a branch of acoustical engineering. So this deals with design and construction of halls or rooms. Hall or rooms are acoustically poor mainly due to distribution of intensity is not uniform, different frequency of sound interfere and reduces the quality. So these two are actually the pictures of world's two best concert halls. The first application of modern scientific methods to architectural acoustics was carried out by Professor Savin in the Fogg Museum lecture room, who then applied this newfound knowledge to the design of Symphony Hall, Boston. We will learn his formula on architectural acoustics in the next lecture. Let's think about there is no surrounding sounds. If there is no ambient sound, how do we feel? Considering our normal practice, probably we can feel uncomfortable and can become disoriented very quickly. One of the best or maybe the worst place to experience this is an anechoic chamber. An anechoic chamber is a room designed to completely absorb reflections of either sound or electromagnetic waves. They are also often isolated from waves entering from their surroundings. This combination means that a person or detector exclusively hears direct sound, so there is no reverberant sounds. Now the question is why we actually need them. What are anechoic chambers used for? Anechoic chambers are typically used in acoustics to conduct research. All sound energy will be traveling away from a noise source with almost none reflected back. Typical anechoic chamber experiments include measuring the transfer function of a loudspeaker or the directivity of sound radiation from industrial machinery. You can see here a F-16 Fighting Falcon in the anechoic test chamber. And this is an anechoic chamber on the campus of Microsoft, the quietest place on the planet Earth. Microsoft actually broke the world record in 2015 with a measurement of minus 20.6 decibel. Human can typically hear sounds above 0 decibel. So as a result, a human would think the surroundings of an anechoic chamber to be void of sound. So the architectural acoustics or the acoustics of the buildings is the branch of science which deals with the planning of a building to provide the best quality audible sound to audience. Any hall having the good acoustics should have the following features. The quality of the speech or music remains unchanged in each and every portion of the hall. The sound produced must be sufficiently loud. There should not be any echo. The reverberation should be proper. There should not be any focus of sound in any part of the hall. The walls should be soundproof to avoid external noise in the hall. Now we will talk about reverberation, a very important term for the architectural acoustics. Reverberation in acoustics is a persistence of sound after the sound is produced. So when a sound is produced inside a building, it expands and gets reflected from all the surfaces. That is from the walls, ceiling and the floor of the hall. Audience will receive a direct sound from the source followed by series of sounds reflected and traveling towards them. These successive sounds will be of diminishing intensity. Therefore, listeners will continue to receive the sound even after the source of sound has stopped emitting. This is called as reverberation. So basically it is the persistence or prolongation of sound in a hall even though the sound source is stopped. This audio clip shows an example of reverberation, clean signals followed by different versions of reverberation with longer and longer decay times. So now the reverberation time is the time taken by the sound wave to fall below the minimum audibility level after the source is stopped, or you can say that to fall to 1/1,000,000th of its initial intensity after the source is stopped. So I is equals to 1 by 10 to the power 6 into I0, where I0 and I is the initial and final sound intensity level. So now if the reverberation time is too low, sound disappear quickly and become inaudible. And if the reverberation time is too high, sound exists for a long period of time and an overlapping of successive sounds results in unclear information. Therefore, for the good audibility, reverberation time should be optimum. So here in this table you can see some optimum reverberation time for some halls. For example, for the conference halls it is between 1 to 1.5 second. For the cinema theater it is 1.3 second. For the assembly halls it is 1 to 1.5 seconds. For the public lecture halls this is 1.5 to 2 seconds. Music concert halls this is 1.5 to 2 seconds, and for the churches it is 1.8 to 3 seconds. So that's all for today, and in my next lecture I will discuss about Sabin's and Eyring's formulae and absorption coefficient of sound.